Okay. So obviously I'm in a different place. I've done 2 classes already today. Hopefully the sound is okay. If anything happens during it, let me know. Either say something or in the chat. I can hear you guys if you talk and ask questions. I had a couple people last class ask a bunch of questions, and it went pretty good. So sorry for all the craziness this week. It's definitely not what I wanted or had planned. I think that in regards to next week, Monday's class is still a little bit up in the air whether or not I'll be back in person or we'll have to do a Zoom class again. I felt pretty good yesterday. My fever kind of finally went away. It came back a little bit this morning. It's been gone most of the day. So if I don't have a fever the next 2 days, I'll be okay to go into class on Monday. If I get a fever at any point, I'll probably have to kind of just play it safe. And I don't think, I mean, I have a negative test result, but I'm still supposed to wait so many hours before I go back into class if I get a fever. So hopefully we'll be in class in person on Monday. But I'll let you know Sunday whether or not that'll be the case. For sure, I'll be back in Wednesday and Friday next week. I don't foresee that being an issue. But yeah, I got pretty knocked out from Saturday to Wednesday. I wanted to do Zoom class Monday and Wednesday, but I woke up, I couldn't get out of bed at points in the day. So I think I'm finally back. So I apologize for kind of all the, I don't know, like, well, we're going to try to have class and not. I'm always trying to be optimistic, but that's maybe a little bit too optimistic. As far as homeworks go, I think the due dates should be fine because the classes we missed, it was not going to be any new Excel stuff that you would need for the current Excel assignment. For the Connect, there's really only one problem, and we'll cover that stuff today. So you're still going to have, that's due next Wednesday, so you're still going to have 5 days to kind of work on that one problem on Connect. You could have done all the other ones already too. So there shouldn't be any real issue there. What I am going to do is try to get up a recorded lecture either later this evening or early in the day tomorrow, which I'd like you to try to kind of get through. I'm going to expect that you've watched or listened to it prior to Monday's class. So just help us kind of catch up a little bit. It's not going to be anything too crazy. It's really actually a lot of the just setting us up to be able to talk about the next topic, which is probability. So I'll kind of have, it'll be shorter than like a usual class period. I think it's probably going to be like 30 minutes, but I'll have that recorded. And then I want you to do, I'll post the chapter 4 Learn Smart. I want you to get that done before class on Monday as well. So, you know, that Learn Smart only should take, 10, 15 minutes. I even suggested to some people for watching that video recording, maybe if you have the free time on Monday, plan to watch it the 30 minutes prior to when we start Monday's class, right? It'd be a nice kind of easy way to kind of jump right into it. And then if you have any questions over anything, you can ask them right away. I mean, it's up to you how you do it, but that's kind of, one option maybe you could do. And I know that kind of puts a little more kind of, some unexpected responsibility on you guys. And I apologize for that, but this is the way things are. We're gonna have to catch up at some point. But today, also for your homework, if you have any like last minute questions, I believe the Excel is due at the end of the day Monday. Feel free to reach out. I've met with a couple people via Zoom. Even yesterday, I had a couple meetings with students who reached out. I was feeling good enough. So I think it went pretty well, or people have sent me their Excel file with like, I have a question on this and this, did I do it right? I'll give it a quick look at. I'm not gonna like go through the entire, homework assignment and grade it and ready to return it to you, but I will look at things that you have questions on whether or not you're doing them correct. So feel free to reach out in terms of that. I think that covers everything. Are there any questions before we kind of jump into today's material? Pull up in the chat. All right, cool. So let's go here. So we'll start today talking about percentiles. Okay. So percentile, I think we might have maybe had just started talking about this on last Friday, if I remember right, but we'll kind of start the discussion again. So if I want, say, the 75th percentile, what I'm really saying, most people draw this percentile back to like test scores, because you've heard, that for SAT scores or all these ISTEP, whatever, you're in the 75th percentile. What does that mean? It means that your test score is better than 75% of the other tests out there, right? Or you're greater than 75% of the other observations. But it's also saying, right, so whatever P% you choose, or 75th percent, then 75% of the other observations have a value less than that, less than yours. If I was in the 75th percentile, also what I could say is, well, I'm actually lower than 100 minus 75, or I'm lower than 25% of the other test scores, right? Or that 25% of the other test scores have a value greater than mine. Okay? So this is, I think a lot of us have heard about percentiles and I think know what they are, but definitionally, that's truly what they mean, right? The 90th percentile means that 90% of the observations are lower than that value, 10% of the observations are greater than that value, okay? So I've seen something, something like this. I was like, these charts, right? You can find your age, your height, go over and find out, okay, which one of these percentiles am I in, right? So how do they calculate those numbers, right? How did they create that graph, right? Where did they come up with these percentile values? So the first thing you would do to create a percentile is however many observations you have, arrange them from smallest to largest. Okay? Once I have them arranged from smallest to largest, I can think, the very lowest observation will be in position 1. The next highest observation would be in position 2, and so on and so forth, all the way up to the last observation, which would be in position lowercase n, which is the number of observations in your sample. So the next thing you would want to do, once you have them ordered, is figure out which position would give you the cutoff for the percentile you're interested in. So if I'm interested in the 80th percentile, what value would be the cutoff for that 80th percentile, such that that value would be better than 80% of the observations, and greater than 80% of the observations and lower than 20% of the observations. Right? So how would I find the position that would give me that value? Because I'm looking at my data after it's arranged, I want to find that value that gives me the 80th percentile by choosing the position that has the number in it that would tell me that's the cutoff for the 80th percentile. Okay? So I can use this equation, and kind of the idea behind why this equation is what it is. Think about it this way. If I had 100 observations and I wanted the 50th percentile, if I just choose the 50th, so I arrange it from smallest to largest, I choose the value in the 50th position. Well, if I have 100 observations, the value in the 50th position would have 49 observations below it and 50 above it. And what I actually want is the value that has 50% of the observations below and 50% above. So I actually kind of need to be in between the 50 and 51st. And so this n+1, that's what it's going to do for me. It's going to make sure that I get a value that's just above that 50th position's value. Okay. So we use this equation. Whatever the size of our data set or our sample is, n, we plug that value in. Whatever percentile we're interested in, so I said 80, I would plug in 80 for P, right? P is just the percentile I'm interested in. And this returns to me the position that I want to go to in my data set that I've arranged from lowest to smallest, smallest to largest. And I can retrieve what that value is. So maybe it would be 42, right? Whatever percentile I'm interested in, whatever the size of my data set is, the position that tells me to find that percentile value is, it's in the 42nd position. So if it's an integer, it's pretty easy. I go to the 42nd lowest number, and that's it. Right? Now, if it's 42.9 or 42.8, it's not an integer, I have to do something called interpolation. Right? So if I have this position is not an integer, I'm in between two positions, right? I'm in between, say, 42 and 43. I need to find, it's not the value that's in the 42nd and the 43rd position, it's going to be somewhere in between those values. Right? And it won't be exactly smack dab in the middle of those two, right? Because 42.8 is a little bit closer to the 49th position than it is the 48th. So I'll walk through some actual data, a couple examples, and hopefully this will make this process makes a little more sense. Right? Nothing in the chat. So let's say I have these metal funds. I order them from smallest and whatever their value is. So this one had a negative valuation. This one has the highest valuation. So I arrange them from smallest to largest. The one thing, I think there might be a connect problem on this. But if you're doing this, be careful if you have negative values, right? They actually have to come first. So you range them from smallest to largest. Here's position 1, 2, 3, etc. Right? So let's say I want the 25th percentile. I plug in to my equation for finding the position. The percentile I'm interested in is 25. The size of my data set here, n, sample size is 10. And I get the position is 2.75. Okay. So 2.75 is the position that I want. What I do is I look at this, this isn't an integer, so it's not nice and easy, right? If this was 3, all I would do is go to the third position and say, oh, 8.09 is the value that is the cutoff for the 25th percentile. But I didn't find 3. I found 2.75, right? So it's a little bit harder. So 2.75, I know that the value for the 25th percentile is somewhere in between the numbers in the second and third position. So it's somewhere in between 8.09 and negative 7.34. Okay? So it's somewhere in between these two values. But if I look at this, I don't just want to look at the middle. I don't want to add them up and divide by 2, simply find the mean, because the position that gives me that 25th percentile is a little bit closer to position 3, right? 2.75, I say a little bit, it's quite a bit closer to position 3 than it is to position 2. So I know whatever value's in position 3, I should be weighting more than the value in position 2, similar to the weighted mean we did last week. So what I'll do is I'll look at whatever my decimal is, and I'll use that as my weight. So 0.75 will be my first weight, and the second weight will be whatever gets me up to 1. Right? So 0.75 would be my first weight. The second weight would be 0.25. Once I have those two weights, now I say, okay, I'm a little closer to position 3, so I'm going to take the value in position 3, 8.09. I'm going to multiply that by 0.75, which was my higher weight, and then I'm going to add to that the position that I'm further from, negative 7.34, times my lower weight of 0.25. Right? So because I was a little bit closer, here I'm going to minimize this a little bit. Because I was a little bit closer to that third position, the value in that third position I weighted with the higher weight. The value in that second position I weighted by the lower weight. And the value for my 25th percentile should be 4.23. Notice that's closer to 8 than it is to negative 7. And it should be. It should have been a little bit closer to the value in that third position. Now, one thing to point out here is in that weighted mean example, we always divided them by the sum of the weights. So notice here I take my weight, multiply it by a value, plus the other weight, multiplied by a value. But the sum of the weights here, using the process I kind of mentioned, taking that decimal 0.75, your second weight is what gets you to 1.25. Well, if my second weight is always what gets me to 1, the sum of my weights will always be 1. Dividing by 1 doesn't change anything, so essentially I don't have a denominator there, right? You don't have to really think about the denominator, okay? But I want to walk through a couple other examples we could see. So let's try this. I've got this. So let's say I'm using that kind of same example here. I can get the marker cap off. There we go. So I've got, let's say the position I come up with is 2.5. So 2.5 is kind of an easier one Because if you look at this, what position am I closer to here? I'm in between 2 and 3, but I'm just as close to position 2 as I am to position 5. So if I was at 2.5, I can think about, I would take each value, hopefully I'm remembering these correctly, and I would multiply them both by 0.5. I know these kind of look like Z's, but they're 0.5. But that's really, multiplying by 1/2 is the same as dividing by 2. It's really just finding the mean of those two numbers. Now it's a little bit trickier, is if I had, say, a position like 2.3 for whatever percentile I'm interested in. Well, there, what are my two weights? Well, I still look at the decimal. The decimal is 0.3. That's my first weight. But my second weight is whatever gets me to 1, so that would be 0.7. So now I've got my two weights. But the one that gets multiplied by the higher weight is whatever position I'm closer to. So the 2.3 is closer to position 2 than it is to 3. So whatever value is in position 2, which if we go back, if you look at the actual slide, the value that's in position 2 is this negative 7.34. So this is the one that actually gets multiplied by the higher of the two weights. So this gets multiplied by 0.7. And then the position I'm further from, which here was position 3, the value in that position, that 8.09, that one gets multiplied by the lower weight, right? So it's not just that I take this weight, 0.3, and multiply it by the higher value, the third position. No. I just use this to get my weights first, and then using these weights, I say, okay, which position am I closer to? Whatever position I'm closer to, the value in that position gets weighted by that higher weight, okay? So I'll kind of put that up here. So if you couldn't see it too clear, you were kind of copying down or writing any of it, here's what I was doing. Okay. Any questions on that before we kind of keep moving forward? I'm trying to keep an eye on the chat. Usually it gives me like a little indicator if someone has a question there. Okay. So finding these percentiles, what we could do, right, is, you might have seen this other, has anyone in any class seen like box and whisker plots? Not even a high school like science class, maybe you've talked about it. Maybe not, but yeah, a couple of times. Yeah. So you've kind of seen it. So what those represent, right, are something we could actually create those using percentiles, okay? So what we're first going to do, if I can get my, there we go. What you could do is find your first, second, and third quartile. So what a quartile is, right, you're really just thinking if I took all my data and I could break it down into 4 sections, quartiles, right, how would I find the cutoffs for those? Well, the end of the first quartile would be the 25th percentile, then the 50th, 75th, and obviously the 100th percentile, which is just your maximum value. So really to get those 3 cutoffs in the middle, I need my first quartile value, my second quartile value, which is really just the median, right? It's the 50th percent, right in the middle. Excuse me. And then my third quartile would be the 75th percent. So you can think of the median as the second quartile, but remember the definition of the median is the value such that it's greater than 50% of the data and less than 50% of the data, which is literally what the 50th percentile means. So we have that there. We could find those 3 values using the same process that we just described, right? The same process that we just walked through with a small data set. We could have found the 25th, 50th, and 75th percentile pretty easily too. We had just found the 25th. So once I have those, what I would do, well, I'll hold off and do all the drawing at once. So I'll use those 3, and I'll show you how we would use those in a second. So the next thing I'm going to do for my box and kind of whisker plot, I'm going to need this thing called the interquartile range. So the interquartile range is sometimes a little more useful. It's more useful than the range a lot of the times, because the range is greatly influenced by extreme outliers, right? If I have an income data set and one person makes $1 million, it's going to make my range huge. But if I'm only looking at the difference between the first quartile or the 25th percent and the third or the 75th percentile, the third quartile, well, now I'm like getting rid of those extreme values. I'm kind of looking more at the middle of the data. So that interquartile range is a better idea of kind of the spread of the data because it's ignoring those outlier values. So I find that interquartile range, which is just the difference between the 75th and the 25th percentile, or quartile 3 and 1. I would then build this lower and upper limit. Okay? This lower and upper limit is going to be, okay, I'm going to go to the very first quartile, and then I'm going to subtract or go back 1.5 times whatever that interquartile range is. I'm then going to add to the third quartile 1.5 times whatever the interquartile range was. I might have said that wrong. Hold on. To find the upper limit, I'm going to take the third quartile and add to it 1.5 times the interquartile range. Okay? So once I build these upper and lower limits, any data points that I have that are outside of those upper and lower limits, I'm going to say this identifies those data points as an outlier, right? And so that would give me kind of some good evidence that maybe I could, I could drop that observation if I'm doing some analysis because it wildly influences some of my statistics, especially in a small data set. And, it really does look like, based off of this box and whisker plot, that it's an outlier, or what's sometimes called a Q-test. So I had this great meme, which is, please don't reject me as an outlier because you are the Q-test, because the Q-test identifies outliers. All right, well, it's pretty cheesy. But so how does this look like? What does this actually look like? So I'll go stop share here. I'll minimize this. And I'll do a little drawing here. So what we're doing, building this box and whisker plot. So I'll give you some actual, let's say we had quartile 1, 2, 3. Right? So let's use the values 50, 75, and 80. So the box part is going to be, you just plot these. All right, so I go, okay, 50, 75, 80. There's the box part. Now I need to get my lower limit and my upper limit. Well, to get that, we said what we would do is you take the first quartile minus 1.5 times that interquartile range. Well, I need to find the interquartile range first. So my interquartile range was just that third quartile minus my first quartile. Or in this case, what, 80 minus 50, or 30. Okay. So I've got 30 as my interquartile range. So now I'll take my first quartile value minus 1.5 times interquartile range of 30. Well, this is 5. So there's my lower limit. I then go, how do I find the upper limit? That was just my third quartile plus 1.5 times the interquartile range. So that would be what, 80 plus 1.5 times 30. All right, I believe that's 125. Okay. So that's how I would build that box and whisker plot. And now what I do, this tells me a little bit about the data. First of all, if I have any data points, let's say I had a value in my data that was at 140, that point lies outside of my lower and upper limit. So I could say that's an outlier, and based on the Q-test, I can exclude this from analysis or whatever else I plan on doing, right? Because based off of the range of data I saw, this seems like an anomaly. It seems like something weird's going on with this. They use this I think I was mentioning this in another class. My brother does stuff with exercise physiology. And they see this sometimes where they see a point, it's this person's blood pressure was way outside the range of the rest of our subject pool. So they're of course going to have different reactions to whatever we have them do. And so maybe we should exclude them from the analysis. Right? Then justification is if they're past this kind of upper limit. Right? Now, what's also kind of nice about this box and whisker plot, and I'm not going to ask you necessarily questions specifically on this, but it is interesting that comes out of it. Notice this median was closer to the third quartile. So what we're saying there is if you see kind of that median closer to that third quartile, well, that means like the right side of the data, the values are closer together, right? So it's kind of like that right tail is shorter than the left tail, right? If I think about the value of the 25th percentile to the relative to the median, it's much further away. So we had like a long left tail here, or we had like a left skewed looking distribution. And then vice versa, if the median was closer to that first quartile, we have like a shorter left tail and a longer right tail, we have like a right skew distribution. And if it's smack dab in the middle, then we have a nice normal distribution, right? So that's how we would kind of build those box and whisker plots, kind of what they mean. If you see them around, it's where they come from. Right? Any other questions on that before we keep moving? Okay. All right. So up to this point, we've primarily, other than when we talked about scatter plots, really only been talking about one variable, right? So this has either been finding the mean of a variable or the variance. But what if we want to know the relationship between two variables, right? So we have two, if one variable goes up, does the other one go down? Does the other one go up? Does the other one not change much at all? And really, once we have two statistics we'll use initially to capture this relationship, right? Whether or not if the number of years of education goes up, does someone's income go up, right? Or does it not change at all, or does it go down? You kind of probably know intuitively that one, but some other ones we might have really not sure. So we'll have the covariance and the correlation coefficient, or shorthand correlations. Now to find the correlation coefficients or the correlations, we first have to find the covariances. So we'll first talk about covariances. So population and sample, right, depending on what type of data we have. So the first one we'll think about, we have two variables, X and Y. Our formula for the covariance, the notation that we'll use is this sigma, right? So I know that we use sigma for the standard deviation, but here notice we subscript it with whatever two variables we're using. So sigma and then X and Y, or if it's education and income, EI, whatever two variables you're using. If you identify that this is a measure of two variables with sigma, sigma no longer then represents a standard deviation, it now represents a covariance between whatever two variables you've included on the subscript, okay? So the process that we're gonna do, and I'll show you this with some data here in a second, but for every single observation, you're going to take the very first, so let's say I have years of education and income, what is my example? I could find the average number of years of education, the average income for those individuals. Y was my income variable. For their first observation, I'd take that person's number of years of education minus the average, and then I would multiply that by whatever the difference was for that person's income and the average income. And then go to the next person, take the difference between their number of years of education and the average education, multiply it by the difference between their income and the average income. I would keep doing this for every observation. Once I get to the very last observation, I would then add them all up, right? From the first to the last observation, I would do all what I just described, add them all up. That's what the summation sign means. And then for a population covariance, I divide by the total number of observations. And just like with the regular variance, not the covariance, but regular variance, when I move to the sample covariance, instead of dividing, it's the same process, but instead of dividing by the total number of observations, I divide by the total number of observations minus 1 that are in my data set. Okay? Once again, that kind of corrects for that bias that's caused by just having a sample of the data. Okay, no questions. All right. So what does this covariance really tell us? Like I said, I'll walk through again so we can kind of understand how this formula is working with some actual data here in just a second. But what is the covariance actually telling us? Well, if it's positive, it's telling us that as X gets higher, Y also tends to be higher. Right? So I wrote here it as the sample covariance between X and Y. So if it's above 0, it's a positive relationship between these two things. If it's below 0, it represents that we have a negative relationship. And if it's about zero, it's where we don't have a relationship. So unlike the variance, the covariance can be negative because we're not squaring anything here, right? There's no, so we could have things below the mean, right? We could be getting negative values up here and nothing's getting squared, okay? So let's look at some actual data. So let's say I was supposed to have like a big white thing that blocked this out initially, but that's okay. So if we had height and weight were the two variables we're interested in. Let's just start out assuming that for a second. I put the first 4 observations just to give you a little bit of insight what's going on, but I have, say, 44,000, right? To find the covariance, what I would do is, well, first, remember I was going to find deviations from the mean up here for each variable. So the first thing you do is find the mean for height, find the mean for weight. It's pretty easy to do. Like if I had this in Excel, right? I could just find the mean height, find the mean weight using that average function, pretty easy. So I broke this down into a couple different steps to show you some stuff. You don't have to break it down as much as I did, but what eventually what I need to do for every single observation is take the difference from that observation's X value and the average value for X, and that observation's value for the Y variable and the average for that Y variable. Right? So for this first person, I did that, their height minus the average height. So they were above the average height. When I look at their difference in their weight and the average weight, 170 minus 187, they were below the average weight. So this one person, this one observation, right? Once I multiply that deviation from the average for the X variable and the deviation in that observation's value for Y and the average Y variable, I get a negative 53, right? Because this was an observation that said this person was above average height, but below average weight. So they were evidence that when X or height was higher, that Y tended to be lower, right? Or they're on opposite sides of the average. Now, we know intuitively that overall, it's probably that the relationship between height and weight is positive, but this one observation was evidence that maybe not necessarily all the time, right? And so what that's going to do is it's going to say, okay, yeah, maybe there is a positive relationship, but every time we see evidence that that's not necessarily the case, it's going to add a negative value to that covariance and just kind of decrease it a little bit so that it shows us that, yeah, they might be positive related, but not to a really great magnitude. Right? So if we look at other observations, though, it would make a little bit more sense. Like this person is a number 3, pretty far below average height, right? Their height minus the average is -5, but they were way below the average weight. I mean, this person was even 100 pounds. This is insane, right? So if we look at how much below the average weight they are, quite a bit, right? But now notice, this person is below the average height and they're below average weight. So this observation is evidence that when height is lower, so is weight. That they're both on the same side of the average, right? They're both below. But notice, negative times a negative, right? This was evidence that there was a positive relationship. When I multiply these two, I get a pretty large positive value added to the numerator of that covariance. And that's because this observation was very strong evidence that when you're shorter, even not a whole lot shorter than the average, that you're quite a bit, your weight falls quite a bit below the average. Now, obviously, some of these observations I might have chose specifically to prove some points, but not everyone's going to be strong evidence of a positive relationship or even evidence of a negative. But what we're trying to get the covariance is going to be is, once we do this for every person, we're going to add these all up. Any one observation could be evidence that there's a negative relationship, or any one could be evidence that there's a very strong positive relationship. But once we add these all up, what our covariance should be is a measure of, over all the observations, what does it look like the average kind of, right? It would kind of give us this average relationship between these two variables, okay? So once we add these all up, I mean, the final step, if it's a sample data, we'd have to divide by n minus 1. So here I think it's 44,000, so 43,999 people we'd have to divide by. But if I go ahead and do that, I'll find the covariance is about 76, right? So not super strong, right? In terms of, I mean, some of these observations were adding like 500. So it must be that even for these really strong positive values that were getting added in, there must have been enough negative observations that had a negative value here, or evidence that height and weight could be on either sides of the averages, that we didn't end up with a really strong, or really high or strong covariance, right? But even 76, and I'm saying strong, like 76 what? Like, what does this covariance really mean? I mean, well, the sign of it means something. The sign of it tells me something, but the magnitude and the power of this covariance really isn't clear, because I don't really know how to even think about what a high covariance would be here. Kind of depends on what the overall like dispersion is in the data, in the two variables. If I even think about what is my covariance units, well, I've got inches and I've got pounds. So when I multiply, the units are inch pounds. Like, I don't know what that is, right? Like if I did years of education income, I'd have what, dollar years? Like, I don't know what these things are. How do I compare across data sets? I can't compare dollar years to inch pounds. Both those things are made up to begin with. Now I'm comparing to made up, it's really hard to use that covariance unless I'm comparing data sets that have the exact same variables, like compare the relationship of height and weight between the US and Canada, right? So it's probably better to do than use this covariance is, well, now that I have the covariance, I'm going to scale it so I can compare across data sets. Okay? So the correlation coefficients kind of saves us and says, okay, you didn't find this covariance for nothing. It's useful, I promise you. You just got to tweak it a little bit to get it to where you can compare across data sets. So we're going to scale it, just like we scaled the variance to become a standard deviation by taking the square root. But here, we're going to do a little bit different, right? So we're going to scale that covariance. So notice here, here's my covariance. We're going to divide it by the standard deviation of each variable to get my correlation coefficient. So the population correlation coefficient, we'll call this Greek letter rho. The sample correlation coefficient, we'll call this lowercase r, right? Or our English kind of letter r. So it kind of follows the normal convention of our other notation. It's a little bit different, okay? So we've got our population, our sample correlation coefficient. It's pretty easy to find. Like once we've calculated the covariance and we've calculated our standard deviations, it's really just a pretty simple formula, really. It's 3 numbers and you're doing some division. Excuse me. Any questions on this before I keep moving? Were there any questions like kind of back here on this covariance, or I want to make sure I'm not moving too quick? We're good? Okay. So this is how we scale it. What is the result of scaling? When we divide by these standard deviations, right? And I should say here, when I say sigma x and sigma y, before I was just writing the standard deviation as, say, sigma. I'm just adding sigma x here as indicating it's the standard deviation for variable x and the standard deviation for variable y. Before, we never had more than one standard deviation, so we didn't have to like label them. You can almost think about subscripts here on variances and standard deviations as you're just labeling what the standard deviation or variance of. Right? So when we scale this covariance by dividing by the standard deviations, a nice property is it limits our correlation coefficient to be between 1 and -1. So why that's the case, if I have time at the end, I'll kind of give you a little quick mathematical, like maybe why. You can go look at the proof. It's not, I don't know if I doubt you want to. But essentially you can kind of think about like, it accounts for the variation that exists in both of the variables. And because just the variation, the variables could influence the covariance, it like is able to scale it back down. I don't know how to give like a great intuition as behind why it does it, but it's not overly important that we know that too much other than, or know why as much as we just know that it does scale between 1 and -1. Like I said, we can go try to read through the mathematical proof, but it's a little bit over this class. But just know that once we divide this standard deviation, it has to be between 1 and -1. 1 being the strongest positive relationship between two variables, -1 being the strongest negative relationship between two variables. And then as we move towards 0 from either side, we're just saying that whether it's a positive or a negative relationship, as we move towards 0, it's getting weaker. Okay. Now, what this is also going to do, you can kind of imagine here, if I take my previous example, my covariance was in inch-pounds, right? Inches times pounds. Well, notice when I multiply the standard deviations, I'll have inches times pounds, so it's inch-pounds over inch-pounds. My units cancel, right? So that's great because now I have a correlation coefficient that is unitless. It doesn't matter what my two variables started out as, I can compare across data sets now because with my correlation coefficient, I don't have any units attached to it. So it's great. So between 1 and -1, it's unitless, and I can start to compare across data sets, right? So I go back to my CDC data, and I remember what my sample correlation coefficient, equation is. We found that covariance was 76. I went back through the data, found the two standard deviations. It's just a matter of plugging these in. 76 divided by about 4 times 43. And I get this correlation coefficient of about 0.45. So we find that there's a positive relationship between height and weight, but the correlation coefficient allows us to say like how strong it is, right? Well, it's not the strongest, right? Strongest is 1. It's not the weakest. The weakest would be 0. It's kind of somewhere in the middle, right? It's almost smack dab in the middle. It's a positive relationship. It's not the strongest. It's not the weakest. It exists, but it's not, it's probably not the driving factor. Right? It is one of the factors, but it's not going to maybe be like something that 100% could accurately predict. Height wouldn't be the thing that could accurately predict weight or vice versa. Okay. I think typically like the rule of thumb, because we'll come up with better ways to determine the relationship between two variables by the end of the course. But I think like a rule of thumb, like 0.7, anytime you see a correlation coefficient above 0.7, you should start to think that's a pretty strong relationship, like above 0.7 or below -0.7, right? Because it has to be less, closer to -1. Now, one thing to be careful on here, if you're working on a problem like this, order of operations matters a lot. So if I type in my calculator 76 divided by 3.96, hit enter, and then hit multiply by 43, I'm going to end up with some outrageously large value. But what I should remember is I know it has to be wrong. Because if I get something that's over 1, I know I messed up because the correlation coefficient has to be between 1 and -1. Okay? So I look at I want to kind of relate this to things we've already talked about. If I think about like a scatter plot, I remember I kind of said we had like a line of best fit. This isn't maybe particularly the most accurate thing, but it's a good way to think about it. Remember when if I did a line of best fit, I can think about the slope of that line tells me about the relationship between X and Y. And so if I wanted like the slope of that line, you can kind of think about that as that's what my correlation coefficient is. It's kind of telling me what the slope of that line would be if I like scaled it to be unitless and be between 1 and -1. Okay. So I'll give you an online quiz today that I want you to do before class on Monday. So I know this might be kind of giving you quite a bit of work here for this weekend, but you had a lot off this week, so you'll have kind of a short video to watch. Get through that chapter 4, Learn Smart, that I'll post after class, and then do this short little online quiz. You can work on it today, work on it before class on Monday if you want to. But like I said, that video shouldn't be too long, so hopefully that won't take you too much time. I think collective, like the 3 of those things should take you less than an hour. So let's say we had like a sample question like this. You might see something like this on your online quiz. I gave you the covariance, I gave you the standard deviations. How would you find the correlation coefficient? Well, you've got the covariance, you've got the standard deviations. Here's your equation. Plug in the covariance divided by the 2 standard deviations. It's that easy. Right? It's not trying to trick you here. Now, one thing that's interesting to notice through the equation, my standard deviations, what did we say the variances always had to be greater than or equal to what? I can never have a variance that's less than 0. So I know my variances are always 0 or positive, which if my standard deviation is just the square root of the variance, I know that my standard deviations always have to be 0 or positive. So if these two values are positive, the sign of the correlation coefficient will be whatever the sign of the covariance is. Remember, the covariance told me whether there was a positive, negative, or no relationship. Well, the correlation coefficient does the same thing. It's just scaling that covariance. So if the covariance is positive, so the covariance here is positive, we know the correlation coefficient has to be as well, so we know we can rule out D. Now we also know the correlation coefficient is scaling the covariance to be between 1 and -1, so we can rule B out right away as well. All right, so it's either A or C. If I actually just go ahead and kind of do the math here, 330 divided by 8.13 times 48.51, I'll end up with about 8.84. Where are we at on time? Okay. And I'll leave this one up here as well, but it's kind of a similar one you can kind of work through. You've got a covariance, you've got two standard deviations. The covariance is positive, so you know the correlation coefficient is positive as well. You know it can't be out of the range of 1, -1, so you can rule out A. You can rule out D because you know it had to be positive. It's either B or C. I believe it's B, not C here. Okay. You actually work the math out. So 0.18 divided by 0.68 times 4.66. All right. So that's just another one. Like I said, maybe before you do the online quiz, if you want to make sure you can reproduce these answers, that would probably be a pretty good idea. And I'm not spending a lot of time on it because honestly, I think once I give you these values, it's pretty easy formula, right? This was a pretty easy one to kind of come up with. So I put in this clip. If you, I don't know, it depends on what your humor is, but I think I usually watch this with everybody in class. It's hilarious. It's a really funny clip from the Jon Stewart show. I don't know how old it is now, but it's an economist who did some work and kind of showing what we can do with these correlations. He was looking at people's beauty and wages, like how much money they make. So it's really, I mean, they do a great job of making it funny. The economist himself, I think he's in on it, but I feel like it also kind of goes over his head. But from what I recall, they don't go into this in the clip. The clip is hilarious, by the way. Please watch it. Just copy and paste that into your URL after class. But what they do is they had all these candidates for some type of employment. They had all their pictures. They ranked them on attractiveness, put them into percentiles based off of like, I don't know, random, like they got a bunch of people to sign up for a random trial, like a experiment or something on might even been on campus to like rank these people. And then they put them in the percentiles. They then kind of sent out these resumes with pictures. And but the key was the resumes were all the same, right? So everyone had the same resume, and then they looked at how many interview requests did this resume get depending on someone's attractiveness. And kind of notice here, like the males was always about one interview, and maybe there's a slight positive relationship between their percentile of attractiveness and the number they got. But notice for women, like the number of interview requests was greatly influenced by kind of what their percentile they're in. So you could like look at this multiple ways. I mean, this is terrible on multiple fronts, right? It's terrible that this is even like a factor in to whether or not people are getting interview requests. We could take it a whole bunch of different ways, but it was pretty interesting. He talks about a little bit in that YouTube clip. It's not a YouTube clip. It's on Comedy Central, I think. Whoever owns the video, it's on their platform. But interesting thing to look into. And kind of showing how if we can look at these correlations, we can start to identify problems in the world. Right? So I will kind of start up on these slides in the additional video I post. I'll start here and kind of work through some of these probability slides. So try to take a look at that before class Monday, and then we'll start wherever I leave off on Monday, talking about probability. Okay. If there's any more questions for me, I'm going to kind of stop just the recording here, but I'll leave open Zoom for a little bit. So if you have any additional questions, you can answer them. All right. So thanks everybody for showing up. Hopefully things will be back a little more back to normal next week. Have a great weekend. If you have any questions or on your homework or want me to look at anything, feel free to email me. And hopefully I'll be in person and see you guys on Monday.